Welcome to this comprehensive tutorial on C-sharp events and delegates. These are essential tools for game development, particularly when managing dynamic user interfaces and robust scoring systems. Understanding them enhances your ability to create interactive and responsive game experiences. We'll explore how C-sharp events and delegates enable loose coupling, a crucial architectural principle. This allows distinct game parts, like game logic and UI, to communicate efficiently without rigid dependencies. This flexibility is key for scalable and maintainable game code. First, let's demystify delegates. Think of a delegate as a type-safe function pointer, a variable holding a reference to a method. The type-safe aspect ensures the referenced method always matches a predefined signature, preventing errors. A delegate explicitly defines the precise signature of any method it can point to. This includes the method's return type and the exact types and order of its parameters. This strict definition ensures compatibility and predictability. Consider a remote control. Each button, like channel up, doesn't perform the action directly. Instead, it acts like a delegate, pointing to a specific function on your television, such as changing the channel or adjusting volume. Pressing the button tells the TV to execute that function. In C#, a delegate operates similarly, acting as a blueprint or contract for methods. It defines what kind of method it can represent, allowing for flexible and dynamic method invocation. Let's dive into a simple code example to illustrate its use. Here, we define our custom delegate, myDelegate. This specifies that any method assigned must return void and accept exactly one int parameter. This strict definition ensures type safety and consistency across our codebase. Next, we create myMethod, which perfectly matches myDelegate's signature. It returns void and accepts an int parameter. Inside, we simply log the provided integer value to the console. This illustrates a method referenced by our delegate. To use our delegate, we declare a variable of type myDelegate. Then, we assign myMethod to this delegate variable. This assignment establishes the crucial link, referencing the specific method we want to invoke later. It's like programming a remote button. Finally, with del referencing myMethod, we can invoke the delegate like a regular method. Calling del with an integer, such as 5, executes the referenced myMethod. This prints value 5 to our console, demonstrating the indirect method call. This process clearly demonstrates a delegate's fundamental role. It acts as a powerful intermediary. You call the delegate, and it, in turn, invokes the method it references. This indirect invocation is a cornerstone of flexible programming, laying the groundwork for events. Now, let's transition to events. Events are a higher-level abstraction in C# built upon delegates. They provide a structured way for different objects to communicate, signaling when something significant has occurred, without needing direct knowledge of each other's internal workings. Events implement the powerful publisher-subscriber model. Imagine a newspaper publisher and its readers. The publisher creates news, and readers are interested. This analogy perfectly illustrates how events facilitate communication between distinct components. The publisher is the entity that initiates communication. In our game, Game Manager acts as the publisher. When a significant state change occurs, like a score update, the Game Manager raises an event. This signals to the system that something noteworthy has taken place. Subscribers are interested in these notifications. Our UI Manager class functions as a subscriber, actively listening for specific events. When an event is raised, it receives the notification and reacts, perhaps by updating a score display or triggering an animation. This creates a responsive system. In C#, an event is declared using the event keyword. This modifier places important restrictions on how the underlying delegate can be used. It ensures the event can only be invoked from within its declaring class, providing a controlled communication channel. Events offer enhanced encapsulation. Only the class that declares an event has the authority to invoke it. This strict control ensures communication flows predictably, preventing external classes from arbitrarily triggering events. This is vital for maintaining a clean and robust architecture. Subscribers' interaction with an event is strictly limited to adding or removing their event handlers. They cannot directly invoke the event themselves. This restriction prevents external classes from improperly triggering an event, upholding the publisher-subscriber model's integrity. Now, let's dive into a practical example, building a game UI and scoring system using events and delegates. This hands-on demonstration shows how these concepts combine to create a responsive and modular game architecture, crucial for any interactive experience. For our scenario, imagine a simple game where we need to continuously display the player's current score within the user interface. This score needs to update dynamically as the player progresses. This task showcases the elegance of event-driven communication. We'll create a Game Manager class to manage the game's score. This class will encapsulate all score logic and act as our event publisher, responsible for notifying other parts of the game when the score changes. It's the central hub for score-related events. Inside Game Manager, we'll declare a static event using the built-in action IntDelegate. Making it static allows easy subscription without a Game Manager instance. Action int is perfect as it takes an integer and returns no value, suiting our score update notification. The choice of action int is ideal because our event's primary purpose is to communicate the new, updated score, which is an integer. Since the event simply notifies subscribers and doesn't require any return value, action int provides the ideal, concise, and type-safe signature. Next, we'll add a private static integer variable named score to hold the current value. Additionally, we'll implement a public static update score method. This method will serve as the primary entry point for other parts of the game to modify the score, ensuring controlled changes. Inside update score, we first update the score variable with the new score. Immediately after, we invoke our onScoreChange event. We use the null conditional operator. Before invoke, this operator is a critical safety measure, ensuring our code is robust. The null conditional operator prevents runtime errors. It checks if onScoreChange has active subscribers. If none, the invoke call is skipped, preventing a null reference exception. This elegant syntax makes your event invocation code much more resilient and error-proof. Now, let's create the UI Manager class. This will be our event subscriber, tasked with updating the score display on the user interface. The UI Manager will listen for score changes from the Game Manager and react by visually updating the score text, ensuring the player always sees the correct score. In UI Manager, we'll need a direct reference to a UI text element. This text component will visually display the player's score on screen. We'll declare a public field for this, allowing easy assignment of the correct UI text object from the Unity editor. We subscribe to GameManager.onScoreChange within the onEnable method. OnEnable is a Unity lifecycle method called when the object becomes enabled and active. Subscribing here guarantees our UI component listens for score changes as soon as it's active, ensuring timely updates. Then, we implement Update Score Display. This event handler signature must precisely match action int. Inside, we take the score value from the event and update the text property of our ScoreText UI element. We prepend score for clear presentation. Crucially, we must unsubscribe from the event in onDisable. This Unity lifecycle method is called when the object becomes disabled or inactive. Failing to unsubscribe can lead to memory leaks, degrading game performance, and causing unexpected behavior. This practice is fundamental for robust event handling. If a subscriber is destroyed but the publisher still holds a reference through the event subscription, that subscriber's memory won't be released by the garbage collector. This persistent reference prevents memory reclamation, leading to a gradual accumulation of unused memory, which is a memory leak. With this setup, any call to GameManager.UpdateScore will automatically trigger the onScoreChange event. This event, in turn, invokes UIManager.UpdateScoreDisplay, ensuring your user interface is always perfectly synchronized with the game's current score without direct dependencies. Now, let's review some essential best practices for cleaner, more robust code. We'll also delve deeper into specific strategies for memory leak prevention, ensuring your game runs smoothly without unexpected performance degradation. Adhering to these guidelines will significantly improve your development workflow. Always use the null conditional operator when invoking an event. This safeguard gracefully handles scenarios where no objects are subscribed, preventing a null reference exception. This small addition makes your event invocation code much more resilient and error-proof, ensuring stability. Unsubscribing from events is critical, especially for objects with different lifetimes. If a subscriber is destroyed without unsubscribing, the publisher still holds a reference. This leads to memory leaks, where allocated memory is never released, eventually impacting performance and stability. For advanced scenarios, consider weak events. These are designed to automatically handle unsubscription, preventing memory leaks even if subscribers are garbage collected without explicit unsubscription. While more complex, they offer a robust solution for specific architectural needs, especially in highly dynamic systems. Remember, C# provides built-in delegate types like Event Handler, Action, and Func to simplify your code. Event Handler is for general events, Action for methods returning void, and Func for methods returning a value. Utilizing these generic delegates often makes your code cleaner and more readable. Events and delegates are incredibly versatile. Beyond scoring, they're perfect for player health updates, where a player health class publishes an event. Similarly, game over events, item collection notifications, or quest updates are all ideal candidates for this powerful pattern, promoting modularity. All these scenarios are perfect candidates for event-driven communication. This approach promotes highly modular and maintainable game code. By decoupling components, you can modify one part of your game without breaking others, leading to a more robust development process and easier debugging. This is a cornerstone of professional game development. Debugging event-related issues is key. A highly effective strategy involves setting breakpoints. Place them where an event is invoked by the publisher and within event handler methods and subscribers. This allows you to step through, confirm events are raised as expected, and verify correct handling by all components. By mastering C# events and delegates, you'll build significantly more robust, scalable, and exceptionally well-organized game systems. These tools empower you to create games that are not only functional, but also easier to expand, maintain, and debug. They are indispensable for any serious game developer aiming for professional-grade code. Thank you for watching this tutorial on C# events and delegates. We hope you found the explanations clear, the examples practical, and the best practices insightful. May this knowledge be a valuable asset as you continue your exciting journey in game development. Keep building amazing things,